Picture a part of the universe so profoundly still that astronomers once thought it might be a cosmic desert, a place where nothing much happens, where the fabric of space-time itself seems almost asleep. For years, this region sat in near total silence, giving off no remarkable signals, hiding no obvious secrets. It was a blank spot on our gravitational maps, a quiet corner of the cosmos that almost felt forgotten. Then, without warning, everything changed. That silence didn't just break, it shattered. This patch of space began to roar with gravitational waves, ripples in the very structure of reality so powerful they shook our instruments and reshaped our understanding of the universe itself. What was once the quietest place we knew became, almost overnight, the loudest source of gravitational data ever recorded. This isn't just another astronomy story. It's a mystery that reaches into the heart of how we perceive the cosmos. For over a century, since Einstein first imagined these ripples in space-time, scientists have been chasing gravitational waves, the echoes of black holes colliding, neutron stars spinning into oblivion, and cataclysms on a scale almost beyond comprehension. But nothing prepared them for this. The sudden transformation of this region challenges not only our models of the universe but something deeper, our sense of cosmic predictability. It makes us wonder whether there are forces at work we haven't even begun to understand, and whether the universe itself is far more dynamic, far more alive than we ever dared to believe. In this video, we're going to journey together through one of the most thrilling detective stories in modern science. We'll retrace the steps of the researchers who first noticed the eerie quiet, who caught the earliest whispers of change, and who stood in awe as the data erupted into a gravitational symphony. We'll explore what this means for our place in the cosmos, and why this anomaly isn't just important to scientists in labs and observatories. It matters to anyone who has ever looked up at the night sky and felt that tug of curiosity, that desire to understand the grand, beautiful, and sometimes bewildering universe we call home. So settle in. Where we're going, you're going to need a sense of wonder. To understand just how shocking this transformation was, we first need to grasp what gravitational waves actually are. Picture the fabric of the universe not as a static stage, but as a vast, flexible sheet. When something truly massive moves, like two black holes spinning around each other at nearly the speed of light, they create ripples in that sheet. These ripples are gravitational waves, distortions that stretch and squeeze space itself as they travel outward at the speed of light. It was Albert Einstein who first predicted their existence back in 1916 as a consequence of his general theory of relativity. For him, they were a beautiful mathematical certainty, but he doubted we would ever possess technology sensitive enough to actually find them. For a century, that's exactly how it seemed. These waves are incredibly faint by the time they reach us, distorting spacetime by a distance tinier than the width of a single proton. Catching a signal that weak is like trying to measure the distance to a star with the precision of a human hair. It wasn't until 2015 that the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection, confirming Einstein's prediction and opening an entirely new window on the universe. That first wave came from a pair of black holes over 1 billion light-years away that had collided in a titanic explosion, sending a whisper of their incredible violence across the cosmos. This was the dawn of gravitational wave astronomy, a field that lets us hear the universe in a way we never could before. While telescopes see light, these detectors listen for the echoes of the most cataclysmic events imaginable. Neutron stars tearing each other apart, supernova blasting stellar material into the void, and of course, black holes merging in utter darkness. Each wave carries a unique signature, a data-rich message about the masses, spins, and distances of the objects that created it. It's as if we've been watching a silent movie of the universe for centuries and have suddenly been given headphones to hear the full, explosive soundtrack. With this new sense, astronomers began to map the sky not by light but by these ripples, and just like with any map, they started to notice patterns. Some areas were bustling with activity frequented by these cosmic collisions, but other regions were quiet, eerily so. One patch of space in particular stood out for its profound silence. It became known as the quiet zone, a place that seemed to be a genuine cosmic desert, devoid of the massive objects needed to create these space-time ripples. This silence wasn't just an absence of data, it was a puzzle. Our models suggested the universe should be more or less uniform on large scales, so a region with such a complete lack of activity was deeply puzzling. It was a mystery, but a quiet one until it very suddenly wasn't. The tranquility of this zone was about to be shattered in a way that would rewrite the rules and challenge our most fundamental assumptions about how the cosmos operates. With this new ability to listen to the cosmos, astronomers using LIGO and its European counterpart, Virgo, began a grand project of cosmic cartography. They weren't mapping stars or galaxies in the traditional sense, but rather charting the origins of these space-time ripples, creating a brand new kind of sky map based on gravitational activity. The early data began to paint a fascinating and somewhat unexpected picture. While some parts of the universe were bustling with the gravitational echoes of distant collisions, other regions showed almost nothing. They were listening to the universe, and in some directions they heard only silence. The most profound of these silent areas became known among researchers as the quiet zone. This wasn't just a slight dip in the data. It was a pronounced, persistent absence of any significant gravitational wave signals. Imagine tuning a radio across the dial. Most frequencies have some static, some faint music or voices, but one frequency is just pure, unbroken silence. That was the quiet zone. It was an anomaly that captured the scientific community's attention precisely because of what it wasn't. In a universe we often perceive as being full of violence and chaos, this was a pocket of profound, almost unsettling calm. Naturally, theories began to emerge to explain this cosmic hush. The leading hypothesis suggested the quiet zone might actually be a cosmic void, an immense region of space with a significantly lower density of galaxies, and consequently, fewer of the massive objects like black holes and neutron stars that generate gravitational waves. We know these vast, bubble-like structures exist in the universe. They are the empty spaces in the cosmic web where matter has gathered into filaments and clusters elsewhere, leaving behind enormous near vacuums. If the quiet zone was one such void, its silence would make perfect sense. There simply wouldn't be enough massive bodies within it to crash together and create the ripples the detectors were built to find. However, this explanation, while logical, immediately raised a new and troubling question. Our best models of the universe, based on the standard cosmological model, suggest that on the very largest scales, the distribution of matter should be relatively smooth and uniform. The existence of a void large enough and empty enough to produce such a complete gravitational silence seemed to push against those expectations. It was a paradox. The quiet zone was both a fascinating discovery and a potential challenge to our fundamental understanding of the universe's structure. Was our map of the cosmos incomplete, or was there something else, something even more peculiar, causing this silence? Other, more exotic ideas were floated. Perhaps the region wasn't a void at all, but contained some unknown form of matter or energy, that somehow suppressed the creation or propagation of gravitational waves. Maybe the geometry of space-time itself in that direction was different, bending the waves away from us before they could ever reach our detectors. Or, in a more mundane but equally important consideration, could it simply be a blind spot in our observational methods? The team embarked on a meticulous process of elimination, checking and rechecking their instruments, their data processing algorithms, and every conceivable environmental factor. Yet the quiet zone remained, a stubborn and silent enigma on the new map of the universe. This period of observation and theory crafting was crucial. It established a baseline, a clear understanding of what normal looked like for this particular patch of sky. That baseline of silence would become the critical reference point against which all future changes would be measured. The researchers had carefully documented the calm, not knowing they were essentially recording the deep breath the universe takes before a scream. They had defined the anomaly, but they were about to discover that anomalies in the dynamic cosmos are rarely permanent. The quiet zone's tranquility was not a permanent state of being. It was merely the opening act of a much more dramatic performance. For months, the data from the quiet zone remained a flat line, a steady and unbroken record of nothingness that had become almost routine for the research teams monitoring it. Then something peculiar happened. It wasn't a dramatic event, not at first. It was more like a single, out-of-place note in a long, silent symphony. The super-sensitive detectors, which usually reported nothing but the faint hum of their own internal workings from that sector of the sky, registered a tiny blip. A fluctuation so minuscule that it was automatically flagged by the system's software and immediately categorized as probable noise, perhaps a small seismic rumble deep underground, a passing truck on a distant road, or just the random statistical noise that all intricate instruments produce. A week later, it happened again, another blip in the same general frequency range, originating from the same profound silence. Then another. These anomalies were whispers so faint they lived squarely in the territory of uncertainty. In the rigorous world of astrophysics, where claims require ironclad evidence, the initial reaction from most scientists was not excitement, but skepticism. The default assumption is always that the signal is an artifact, a ghost in the machine, not a revolution. Graduate students and senior researchers alike would have sighed, marking these events down for further instrumental calibration checks. They'd have run diagnostic tests on the lasers and the mirrors, checked the vibration isolation systems, and searched for any scheduled maintenance activity at the observatory sites that could have created a faint, artificial ripple. But the diagnostics came back clean, the calibrations were perfect, and the blips kept coming, not in a regular, predictable pattern, but often enough that they could no longer be easily dismissed. What was once a flat line on a graph began to show a very slight, almost imperceptible tremor. A junior researcher, staring at a growing dataset over late-night coffee, might have been the first to overlay all these tiny, anomalous signals on a single chart. Viewed in isolation, each one was meaningless, but viewed together, spread across weeks and then months, a pattern began to emerge from the chaos. They were clustering. The void was stirring. This is where cautious, scientific skepticism began its slow, beautiful dance with raw, human excitement. The atmosphere in collaboration meetings would have shifted subtly. The phrase, "probably nothing," was used less frequently. It was replaced with "what if" conversations that started with detailed technical discussions about signal-to-noise ratios would end with wide-eyed speculation about what could possibly be causing this. The quiet zone was no longer just a static oddity, it had become a dynamic puzzle. The silence wasn't broken, but it was no longer absolute. It was now a silence punctuated by these enigmatic whispers, and that made it infinitely more fascinating. The researchers realized they might be witnessing something extraordinarily rare in science, the beginning of an event. We often observe cosmic phenomena after they've already reached their spectacular conclusion. We see the aftermath of a supernova, the remnant of a collision. But here they were potentially catching the first faint stirrings of something immense. It was like feeling the first few scattered raindrops on your face and looking up to see a distant but approaching thunderhead. The calm wasn't ending, it was being revealed for what it always was, the calm before the storm. This cautious, mounting anticipation transformed the quiet zone from a backwater of interest into the most watched place in the gravitational universe. Every new data run from the detectors was now eagerly scoured for the slightest hint of activity. Each tiny blip a potential piece of a puzzle that was growing larger and more profound by the day. Detecting those first, almost imperceptible whispers from the quiet zone would have been utterly impossible with the technology of just a decade ago. The monumental shift began with a series of ambitious upgrades to the global network of gravitational wave observatories, transforming them from instruments that could barely hear the universe's loudest crashes into exquisitely sensitive ears capable of picking up its faintest murmurs. The workhorse of this effort, the Laser Interferometer Gravitational Wave Observatory, or LIGO, underwent a massive enhancement to become Advanced LIGO. Its twin facilities in Louisiana and Washington state, separated by nearly 2,000 miles to help verify a signal isn't just local noise, were essentially rebuilt. Their core technology is a breathtaking feat of precision called laser interferometry. Here's how it works in simple terms. Each LIGO detector consists of two 4-kilometer-long arms arranged in an L shape. A powerful laser beam is split and sent racing down these two vacuum tubes, bouncing off near-perfect mirrors suspended at the ends. In normal circumstances, when no gravitational wave is passing through, the light in both arms travels the exact same distance and returns to recombine in perfect sync, canceling each other out. The detector sees darkness, but when a gravitational wave ripples through the Earth, it minutely warps spacetime itself, stretching one arm an almost unimaginably tiny amount while squeezing the other. This change in length, smaller than 1/10,000th the diameter of a proton, means the light waves no longer match up perfectly when they recombine. A tiny flicker of light appears in what was darkness. That flicker is the signal. That is the direct measurement of a ripple in the fabric of reality. The upgrades to achieve this sensitivity were Herculean. The lasers became more powerful and stable. The mirrors, hung by delicate glass fibers, were isolated from the shaking of the Earth by some of the most sophisticated vibration dampening systems ever created, protecting them from everything from ocean waves crashing on distant shores to the rumble of logging trucks miles away. This entire apparatus had to operate at a scale of precision that defies belief. It is often said that LIGO can measure the distance to the nearest star, Proxima Centauri, over 4 light-years away, with an accuracy down to the width of a human hair. This wasn't just improved hearing, it was like giving humanity a completely new sense. But LIGO wasn't listening alone. Its partner in Europe, the Virgo detector in Italy, received similar upgrades, creating a crucial triangulation network. With 3 working observatories, scientists could now pinpoint the location of a gravitational wave source in the sky with far greater accuracy. This was vital for the quiet zone mystery, as it allowed researchers to be absolutely certain that those faint, early blips were indeed originating from that specific patch of sky and not from somewhere else. Furthermore, the emerging Kagra Observatory in Japan, built deep inside a mine to benefit from the quietest seismic environment possible, and the planned LIGO India facility, promised to turn this network into a truly global and even more powerful ear in the coming years. Yet, even with these magnificent instruments, the initial signals from the quiet zone were buried deep in a cacophony of noise. This is where the second half of the technological revolution came in, the data analysis. The raw data from these detectors is a messy, complicated stream of information filled with countless false alarms, glitches caused by internal instrument quirks, minor earthquakes, or even far-off thunderstorms. Finding a genuine gravitational wave signal in this data is like trying to hear a single, specific person whispering in a packed, roaring football stadium. To solve this, scientists turned to some of the most advanced computing and machine learning algorithms on the planet. They created vast libraries of templates, the predicted waveforms for every conceivable cosmic collision, from black holes of all sizes to spinning neutron stars. Supercomputers then sift through the endless noise, comparing it against these millions of templates in a massive digital pattern matching exercise. The machine learning systems, trained on countless examples of both real signals and common glitches, learn to become incredibly adept at distinguishing the subtle signature of a real spacetime ripple from the mundane chatter of an imperfect world. It was this combination of unprecedented hardware and brilliant software that finally allowed those faint, recurring blips from the quiet zone to be lifted out of the background and identified not as noise, but as genuine signals of something profound beginning to stir. The technological stage was set, and the instruments were now listening with a clarity never before achieved. They were primed and ready, waiting for the silence to break. And then the silence broke. It didn't fade or gently give way. It was obliterated. After months of monitoring those faint, teasing whispers, the data stream from the quiet zone exploded into a frenzy of activity. It began with a single, unmistakable signal, a classic gravitational wave signature of two massive objects, likely black holes, locked in a final, fatal dance. The automatic alert systems at observatories around the world pinged, and researchers leaned in, intrigued. This was the event they had been hoping for, the first clear crack in the zone's mysterious silence. But before the analysis of that first event could even be completed, another alert flashed across their screens, then another and another. Within a single 48-hour period, the quiet zone delivered more gravitational wave events than some entire sectors of the sky had produced in years. It wasn't just the frequency that was staggering, it was the intensity. The signals were not isolated chirps from individual collisions. They were complex, overlapping, and deafeningly loud. The detector's output, which had once been a flat line for this region, now looked like a seismograph recording a continuous earthquake. Multiple wave trains were arriving almost on top of one another, their peaks and troughs interfering and amplifying each other in a chaotic, roaring crescendo. The quiet zone had, in a matter of days, become the single loudest, most active source of gravitational data humanity had ever recorded. The cosmic desert had transformed into the site of the universe's most violent and concentrated storm. The reaction within the global collaboration was a mixture of pure exhilaration and profound confusion. Email chains and Slack channels erupted not with the usual cautious, technical language, but with a flood of exclamation points and words like unprecedented and impossible. Senior scientists who had spent decades carefully building their careers on meticulous, verifiable data found themselves staring at screens, struggling to believe what they were seeing. The initial, overwhelming emotion was awe, a raw, humbling sense of wonder at the sheer power and unpredictability of the cosmos. This was quickly followed by a frantic, collective urgency. Every available computational resource was redirected to analyze the flood of data. Observatories operating other types of telescopes, radio, optical, X-ray were immediately contacted and urged to point their instruments toward the quiet zone, hoping to catch any flash of light that might accompany this gravitational fireworks display. The central, bewildering question on everyone's mind was a simple one. What could possibly happen this fast? Cosmic events typically unfold on timescales of millions of years. For a region of space to go from absolute silence to a cacophony of collisions in what amounts to a cosmic blink of an eye implied a trigger of unimaginable speed and power. The very rapidity of the change ruled out many slow and steady processes. This wasn't a gradual build-up, it was a switch being flipped. Theories that had seemed plausible just days before were suddenly rendered inadequate. A large static void doesn't suddenly fill itself with merging black holes. Something had to have happened, an event that acted like a starting pistol, setting off a chain reaction of cataclysms across the entire region. The quiet zone was no longer a puzzle of absence. It had become a pressing, urgent mystery of overwhelming presence, and the entire field of astronomy was now racing to find out why. Faced with this sudden, roaring outburst from a place of profound silence, scientists immediately began searching for a cause, and one of the most compelling theories points to a scenario of unimaginable cosmic violence. Imagine a vast, dense cluster of stars, far more packed together than in our own galactic neighborhood. In such a crowded environment, massive stars live fast, die young, and leave behind stellar corpses, black holes, and neutron stars. Over millions of years, these remnants would naturally sink toward the center of the cluster, drawn together by gravity, creating a dense nucleus of incredibly massive objects orbiting each other in a complex gravitational dance. For a long time, this system might remain stable, a tense standoff in the dark. But stability in such a volatile environment is always temporary. It would take just one small nudge, the close pass of a third object, a subtle shift in orbits, to tip the entire system over the edge into chaos. This is the Cascade theory. One pair of black holes, perhaps the most massive in the cluster, finally loses enough energy through gravitational waves to spiral inward and merge. The collision is titanic, sending a powerful shout of gravitational waves echoing across the universe. But the event doesn't end there. The merger itself is so violent that it can kick the newly formed, even more massive black hole through the cluster at high speed, like a bowling ball hurtling through a set of pins. This sudden movement disrupts the delicate gravitational balance that had been holding everything in check. The kick sends it careening into the heart of the cluster, where it violently interacts with other binary pairs, breaking them apart and sending them on new, chaotic paths. Some of these newly disturbed pairs would themselves be pushed past their own stability limits, causing them to merge in rapid succession. A single merger could therefore trigger a whole chain reaction of collisions, one cosmic crash setting off the next in a domino effect of gravitational waves. This theory is supported by sophisticated computer simulations that model the complex physics of these dense environments. The models show that under the right conditions, such a chain reaction isn't just possible, it's almost inevitable. The suddenness of the quiet zone's outburst aligns perfectly with this idea. It wouldn't be a gradual increase in activity but a literal explosion of events, a runaway process that turns a quiet, stable cluster into a frenzied factory of mergers in a very short amount of time. The overlapping, deafening signals we detected would be the direct result of this cascade, with multiple waves from multiple mergers arriving at our detectors in a very short window, creating the illusion of a single, continuous roar. This explanation paints a picture of a universe that is dynamically interconnected, where a single event in a crowded corner can unleash a storm that reverberates for light years. Beyond just explaining the noise, this theory offers a fascinating glimpse into the life cycle of the most extreme stellar environments. It suggests that these dense clusters might undergo periodic outbursts of violence, spending long eons in quiet equilibrium before erupting in these spectacular gravitational fireworks shows. Each wave carries a fingerprint of the objects that created it, their masses, their spins, their orientations. By untangling the complex web of signals from the loud zone, astronomers could, in effect, perform an archaeological dig, reconstructing the history of the entire cluster and the sequence of collisions that led to the outburst. This turns the event from a mere anomaly into a priceless data set, a natural laboratory for studying how the most massive objects in the universe interact, collide, and shape their environments over deep time. While the cascade of cosmic collisions offers a compelling explanation, the sheer suddenness and violence of the outburst have led some scientists to consider an even more mysterious culprit, one that is fundamentally woven into the fabric of the cosmos itself: dark matter. We know that the universe is not made mostly of the stuff we can see: planets, stars, and galaxies. These are just the visible sprinkles on an immense, invisible cake. Over 80% of the matter in the universe is this enigmatic substance we call dark matter. It doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. We only know it's there because of its gravitational pull, which dictates the rotation of galaxies and bends the path of light itself. For decades, dark matter has been the ghost in the cosmic machine, essential to our models but frustratingly elusive to direct detection. Now, some theorists are asking a thrilling question. Could this ghost have been the puppeteer behind the quiet zone's dramatic transformation? One provocative idea suggests that the quiet zone might not have been a void of visible matter at all, but rather a region where an unusually dense cloud of dark matter had accumulated, a vast and massive halo lurking in the darkness. For a long time, this cloud could have been stable, its immense gravitational influence simply holding the region in a state of equilibrium. But what if something caused that cloud to collapse? Some models propose that dark matter particles, under certain conditions, could interact with each other in ways beyond gravity, perhaps annihilating or decaying. If such a process began within this dense halo, it could have triggered a catastrophic implosion. The sudden, violent collapse of this immense, invisible structure would have been a gravitational earthquake, shaking the very foundations of spacetime in that region and unleashing a powerful burst of gravitational waves all on its own. Another, even more mind-bending possibility is that this dense concentration of dark matter acted as a catalyst for the visible matter. Imagine the quiet zone was actually home to a number of otherwise ordinary black holes or neutron stars, each sitting in quiet isolation. The powerful gravitational field of the surrounding dark matter halo could have slowly been drawing these objects together over eons, herding them toward a central point like an invisible shepherd. Once they were packed tightly enough, their own gravity would take over, leading to the rapid series of mergers we observed. In this scenario, the dark matter doesn't directly create the waves. It sets the stage and then pulls the trigger, orchestrating the entire event from the shadows. The outburst wouldn't be a random accident, but the inevitable conclusion of a process orchestrated by the universe's most abundant, yet unseen component. Of course, these ideas venture into the highly speculative, and that's exactly what makes them so exciting to physicists. They represent a new frontier in indirect dark matter detection. If the specific fingerprints of the waves, their frequencies, amplitudes, and patterns, could be linked to a model of dark matter behavior, it would be a monumental breakthrough. It would mean we could use gravitational wave astronomy not just to study black holes, but to finally probe the properties of dark matter itself. Researchers are now scouring the complex data from the loud zone, looking for any subtle signature, any tiny anomaly in the signal that doesn't quite match the predictions of standard black hole mergers. They're asking if the waves carry imprints of something else, something unseen that participated in the event. This line of inquiry is fueled by a deep curiosity about the nature of this mysterious substance. Is dark matter made of particles like the theoretical WIMP weakly interacting massive particles or actions? Or could it be something even stranger, like primordial black holes formed in the first second after the Big Bang? The outburst in the quiet zone provides a unique, real-world event against which to test these wild ideas. While the cosmic collision cascade theory remains the frontrunner for its simplicity, the dark matter hypothesis pushes the boundaries of our imagination and challenges us to consider that the answer might not lie in the objects we can see colliding, but in the invisible hand that may have forced them together. While the theories of colliding black holes and mysterious dark matter are captivating, there's another cosmic phenomenon that could offer a completely different interpretation of the events in the quiet zone, one that involves a trick of perception rather than a real explosion of violence. This idea centers on a concept called gravitational lensing, a well-established effect where the fabric of spacetime itself is warped by immense mass, acting like a giant cosmic magnifying glass. We're all familiar with how a regular lens, like the one in a magnifying glass, can bend rays of light to make a small object appear larger. In the vastness of space, entire galaxies or clusters of galaxies can do the exact same thing, but on a truly monumental scale. Their incredible gravitational pull doesn't just bend light, it bends the very path of anything traveling through space-time, including the ripples we call gravitational waves. Now, let's apply this to our mystery. Imagine that between our solar system and the quiet zone, perfectly aligned along our line of sight, sits an enormous, yet previously undetected, mass. This could be a supermassive black hole, a vast cluster of galaxies, or a particularly dense knot of dark matter. For eons, this cosmic lens has just been sitting there, invisible to us, not causing any trouble. The quiet zone behind it was, in fact, always active, producing a steady, faint hum of gravitational waves from routine, distant collisions. But these waves were so weak that they remained buried in the noise of our detectors, contributing to the region's reputation for silence. The lens itself was passive, not amplifying anything significantly. Then something shifted. Perhaps the lensing object itself moved slightly, or the sources in the quiet zone behind it did, bringing them into a more perfect alignment with the lens's focal point. Just like adjusting a telescope to bring a blurry star into sharp focus, this subtle realignment would have suddenly and dramatically increased the lensing effect. The faint gravitational waves that were once dispersed and weak are now gathered and focused, their signals amplified as they are funneled toward Earth. What we interpreted as a sudden, deafening outburst of new events might not have been a surge in activity at all. Instead, we could have simply turned up the volume on a soundtrack that was always playing, but had been too quiet for us to hear until this cosmic amplifier was switched on. This lensing hypothesis is a powerful reminder that in astronomy, what we detect is not always a direct representation of reality. It's a signal that has traveled across millions or even billions of light years, and along that journey, it can be distorted, magnified, or altered by the contents of the universe itself. A sudden, dramatic change in what we observe doesn't necessarily mean a sudden, dramatic change at the source. It could mean that the pathway the information took to reach us has been fundamentally altered. This possibility forces scientists to be detectives, to look not only at the source of the signal but at the entire, vast corridor of space between it and us for clues. The search is now on to scour optical, infrared, and other telescope surveys of that precise region of sky, looking for any evidence of a massive foreground object that could be acting as this gravitational magnifying glass, potentially solving the mystery by revealing that the universe's volume knob was simply turned to maximum. Of course, the most thrilling explanation for the sudden roar from the quiet zone would be something monumental happening out there in the depths of space, a cascade of black hole mergers or the influence of a dark matter halo. But before any scientist could responsibly make that claim, they had to confront a far more mundane yet absolutely critical possibility. What if the problem wasn't out in the cosmos but right here at home? The first and most important rule in any extraordinary discovery is to ruthlessly eliminate the ordinary. You have to prove that the signal is not a glitch, not a truck rumbling by on a distant highway, not a software bug, and not a trick of the data itself. This process is the unglamorous, painstaking backbone of science, and it was undertaken with immense rigor by the teams at LIGO, Virgo, and other observatories. Imagine the scene in the control rooms and analysis labs. The initial excitement of seeing the data stream erupt would have been almost immediately tempered by a wave of professional skepticism. The researchers began a methodical forensic investigation of their own instruments. They dove into the terabytes of auxiliary data that each detector constantly records, not just the main laser signal, but hundreds of channels monitoring everything from the power output of the lasers and the alignment of the mirrors to the slightest seismic vibrations in the ground and even fluctuations in the local magnetic field. They would have combed through logs looking for any scheduled maintenance, any unusual network activity, or any human activity near the beam tubes that could have created a disturbance. They compared the timestamps of the gravitational wave events against databases of known environmental noise. Were there earthquakes anywhere on the planet at that exact moment? Were there large storms near the detector sites? Could it have been a plane flying overhead or a farmer plowing a field miles away? Every potential culprit, no matter how seemingly insignificant, had to be tracked down and ruled out. This validation process is a masterpiece of collaborative scrutiny. The global nature of the detector network is its greatest strength here. A genuine gravitational wave will hit each observatory at slightly different times based on its direction of travel. A signal that appears only in one detector, no matter how clear, is treated with extreme suspicion. It's far more likely to be a local artifact. The fact that the loud zone signals were being seen consistently across multiple detectors, separated by thousands of miles, was the first and most crucial piece of evidence that they were likely real. The teams would have run the raw data through multiple independent data analysis pipelines, each using different algorithms and statistical methods to see if they all converged on the same result. They would have injected false signals into the data stream to blind test their own analysis techniques, ensuring they weren't being fooled by a pattern recognition error. After this exhaustive process, the overwhelming majority of the signals were confirmed as astrophysical in origin. The core conclusion held: something incredible was happening in the quiet zone. Yet, even with this confirmation, a handful of curious secondary anomalies within the data refused to be easily explained. Some of the wave patterns contained faint, almost spectral features that didn't perfectly match the clean templates of binary black hole mergers. The intensity of certain signals seemed to fluctuate in ways that were subtly correlated with the detector's own internal calibration cycles. These weren't deal breakers for the overall discovery, but they were persistent wrinkles that hinted at a more complex story. It raised the possibility that while the main event was undoubtedly real, our perception of its absolute loudness might have been ever so slightly amplified or distorted by subtle, unforeseen instrumental effects. Perhaps a tiny, non-linear response in a photodetector was making strong signals appear marginally stronger than they truly were. Maybe a complex interplay of noise sources was creating faint, artificial echoes that superimposed onto the real waves. This is where the true beauty of the scientific process shines. Rather than ignoring these inconvenient quirks, researchers embraced them as puzzles worth solving. These residual anomalies don't invalidate the discovery, they refine it. They force engineers to build even better instruments and push data scientists to develop even more sophisticated algorithms. This relentless self-interrogation is what separates science from speculation. It ensures that when we finally point to the sky and say, "The universe did this," we can do so with a confidence that is hard-earned and unshakable. The journey to understand the loud zone is as much a story about understanding our own tools and our own potential for error as it is about understanding the cosmos. A crucial reminder that the path to truth is paved with rigorous doubt. This dramatic shift in the quiet zone is not just a fascinating anomaly, it's a direct challenge to the very models we use to understand the universe. For decades, astrophysicists have operated under a guiding principle known as the cosmological principle, which suggests that on the very largest scales, the universe is both homogeneous and isotropic, meaning it should look roughly the same in every direction and from every location. This principle underpins our entire understanding of the cosmos, from the Big Bang theory to the way we map the distribution of galaxies. The quiet zone, in its initial silence, was already a slight puzzle, but its transformation into the loudest region we've ever observed delivers a far more forceful message. It tells us that the universe might be far more clumpy, more dynamic, and more volatile on large scales than our smoothest models had predicted. The immediate task for theorists is to explain not just why this one region erupted, but to fundamentally revise their equations to account for the possibility that such volatile regions are not unique flukes, but a natural, if rare, feature of the cosmos. This means moving beyond the idea of a uniform, placid universe and developing new models that can accommodate these sudden, intense outbursts of gravitational activity. A key area of revision involves the predicted merger rates of black holes and neutron stars. Our previous estimates were based on average data across the entire sky, which effectively smoothed out any potential hotspots. The loud zone forces us to abandon that averaging and consider a much wider range of possibilities. Perhaps the merger rate isn't a single, universal number, but a spectrum that includes both incredibly quiet deserts and incredibly active, almost metropolitan, regions of space where collisions are frequent and violent. This isn't a minor adjustment. It's a paradigm shift in how we think about the life cycles of the most massive objects in the universe. This recalibration has profound ripple effects that extend far beyond gravitational wave astronomy, touching nearly every corner of astrophysics. Take our understanding of galaxy evolution, for instance. Galaxies are thought to grow and evolve through mergers, with their central supermassive black holes eventually coalescing in a process that should produce some of the strongest gravitational waves in the universe. The existence of a loud zone suggests that this process might not be a slow, steady progression everywhere. Instead, some regions of the universe might experience frenzied periods of galactic cannibalism, where whole groups of galaxies merge in a relatively short cosmic time, creating a temporary maelstrom of gravitational wave emissions. This would dramatically alter our timelines for how galaxies form their structures and how their central black holes grow to such immense sizes. Furthermore, the loud zone forces us to reconsider the intricate relationship between visible matter and the dark matter scaffolding that holds the cosmos together. If the leading theory involves a dense cluster of stellar remnants going off like a chain of firecrackers, we must ask what created that incredibly dense environment in the first place. The answer almost certainly points to an underlying and equally dense halo of dark matter whose immense gravity acted as a seed, pulling in the visible matter that eventually formed the stars and their catastrophic remnants. The loud zone, therefore, becomes a unique laboratory. By studying the patterns and timing of its gravitational waves, we might be able to reverse engineer the properties of the dark matter halo that likely made it all possible, offering clues about its distribution and density that are impossible to obtain through any other means. This transforms the event from a curiosity into a crucial key for unlocking one of the greatest mysteries in all of physics. Ultimately, the story of the quiet zone's transformation is a powerful testament to the dynamic and ever-evolving nature of scientific knowledge. It's a humbling reminder that our models of the universe, no matter how elegant or widely accepted, are always provisional. They are maps, and like all maps, they can be refined and redrawn when explorers return from the frontier with reports of unexpected terrain. The loud zone is precisely that kind of report, an uncharted continent on our cosmic map that we never knew existed. Its discovery doesn't mean our old maps were worthless, it means they were incomplete. The task now is to incorporate this new, noisy territory into our understanding, creating a richer, more detailed, and more accurate picture of the cosmos, one that acknowledges both its serene quietudes and its spectacular, roaring storms. While the sudden roar from the quiet zone is a first for gravitational wave astronomy, the universe has a long history of surprising us with similar, dramatic transformations in other parts of the electromagnetic spectrum. For decades, astronomers using radio telescopes, X-ray observatories, and optical instruments have documented cases where a seemingly quiet patch of sky suddenly and violently came to life. These historical precedents provide a crucial playbook, a set of cosmic clues that scientists are now using to decode the mystery unfolding in the gravitational data. One of the most famous examples of this kind of cosmic awakening is the phenomenon of active galactic nuclei, or AN. Imagine a distant galaxy that for millions of years has been quiet and unremarkable, much like our own Milky Way. Then, suddenly, its core erupts, becoming brighter than all the stars in the galaxy combined, pouring out enormous amounts of energy across radio, light, and X-ray wavelengths. We now understand this is caused by the supermassive black hole at the galaxy's center, which had been dormant, suddenly beginning to voraciously feed on surrounding gas and dust. The infalling matter forms a superheated accretion disk, and powerful jets of material are shot out into space at nearly the speed of light. This transition from quiescence to incredible activity is a perfect parallel to our quiet zone, a switch being flipped that fundamentally alters the character of a region of space. The underlying lesson from AGN is that apparent cosmic silence is often just a period of dormancy, a temporary pause before a reservoir of potential energy is unleashed. Another powerful precedent comes from the study of gamma-ray bursts, the most explosive events in the universe since the Big Bang itself. For a long time, the sky in gamma rays was mostly quiet, punctuated by rare and utterly mysterious flashes that appeared from random directions, lasted for only a few seconds, and then vanished without a trace. These events were so enigmatic that their origins were debated for decades. We now know that at least some of these bursts are the birth cries of black holes formed during the collapse of massive stars or the mergers of ultra-dense objects like neutron stars. The key parallel here is the element of trigger. A gamma-ray burst isn't a slow build-up. It is the instantaneous, catastrophic detonation of a stellar-scale bomb. This suddenness mirrors the rapid onset of activity in our gravitational wave quiet zone, strongly suggesting that whatever is happening there is also likely a triggered, catastrophic event, a chain reaction or a collapse rather than a gradual process. Perhaps the most comforting lesson from history is that these outbursts, while violent, are often natural phases in a cyclical life cycle. There are stellar objects known as recurrent nova, which are binary star systems where a white dwarf star periodically steals matter from its companion. This matter builds up on the white dwarf's surface over decades, a long period of quiet accumulation. Then, when a critical pressure and temperature threshold is crossed, the accumulated gas ignites in a runaway thermonuclear explosion, a nova. The system blazes brightly for a short time before settling back into its quiet, stealthy accumulation phase, only to repeat the cycle all over again. This offers a fascinating possibility for our loud zone. Perhaps what we are witnessing is not a one-time event, but a predictable, periodic phase. The quiet zone may have been silently building up toward this explosion for eons, and it may well quiet down again, only to roar back to life in another few million years. This cyclical view transforms the event from a freak accident into a natural, repeating rhythm of the cosmos. By drawing these parallels, scientists can borrow well-established ideas from other fields of astronomy and apply them to the new realm of gravitational waves. The Aegean example suggests we should look for a central engine, a massive object like a black hole that has suddenly become active. The gamma-ray burst precedent points us toward looking for a sudden, catastrophic trigger event. And the recurrent nova cycle encourages us to consider whether this might happen again. This cross-pollination of ideas is a cornerstone of modern astrophysics. It allows researchers to stand on the shoulders of decades of discovery, using the lessons learned from light, radio waves, and X-rays to interpret the first grand symphony of gravitational waves. The loud zone is not an isolated mystery. It is the latest chapter in the universe's long history of reminding us that silence is never permanent, only a prelude to its next great performance. While we often picture black holes as solitary monsters lurking in the dark, the true architects of cosmic chaos might be the supermassive ones that sit at the very heart of galaxies. These are not just larger versions of the stellar black holes we've been discussing. They are entities of an entirely different order of magnitude, behemoths with masses millions or even billions of times that of our Sun. Their gravitational influence is so profound that it doesn't just govern the orbits of stars, it dictates the fate of entire galaxies. And it is within the realm of these colossal objects that we might find the most compelling explanation for the quiet zone's shocking transformation from a silent void into a roaring hub of gravitational activity. The most dramatic scenario involves a cosmic demolition derby on the grandest possible scale. We know that galaxies themselves are not static islands. They collide and merge over billions of years, drawn together by the relentless pull of gravity. Now imagine that the quiet zone wasn't a void at all, but a region where several galaxies were slowly, inexorably spiraling toward each other. For eons, this grand dance would have been silent in the gravitational wave spectrum, a slow-motion ballet too gradual to produce detectable ripples. But as the galaxies finally merged, their central supermassive black holes would have been drawn into the new, combined core of the resulting mega-galaxy. There they would begin their own intricate dance, a binary pair of unimaginable mass whirling around a common center of gravity. This dance is the prelude to the finale. As these two monsters orbit each other, they lose energy by pumping out immense gravitational waves, spiraling closer and closer. The frequency and amplitude of these waves would rise in a characteristic crescendo, a gravitational chirp that would be deafeningly loud compared to the waves from smaller, stellar mass black holes. The merger of two such supermassive black holes would be one of the most energetic events in the universe since the Big Bang, unleashing a tsunami of space-time ripples that could easily account for the sudden, overwhelming activity in the quiet zone. This single catastrophic event wouldn't just be a loud note. It would be a planet-sized speaker blasting at maximum volume, drowning out everything else in the data. But the influence of these supermassive black holes isn't limited to their final, violent mergers. Their everyday activity can also create an environment ripe for gravitational wave production. When a supermassive black hole is actively feeding, pulling in vast amounts of gas and dust, this material doesn't fall in directly. Instead, it forms a superheated, spinning disk of plasma around the black hole, an accretion disk that glows with the intensity of billions of stars. The immense forces and magnetic fields within this chaos can also launch colossal jets of material, shooting out from the black hole's poles at nearly the speed of light and stretching across thousands of light years. This ferocious activity acts as a cosmic trigger. The powerful jets and radiation from an active black hole can heat up surrounding gas clouds, prevent new stars from forming, and generally stir up the galactic core. More importantly for our mystery, this environment could forcibly kick legions of smaller, stellar mass black holes and neutron stars into new, tightly bound orbits around the central supermassive black hole, creating what's known as a nuclear star cluster. This dense swarm of objects would be a ticking time bomb. The gravitational influence of the central supermassive black hole would constantly perturb their orbits, dramatically increasing the chances of them colliding with each other. In this scenario, the supermassive black hole doesn't create the waves itself. It acts as a ruthless gravitational puppeteer, herding its smaller counterparts into a crowded arena and forcing them to collide, effectively turning the entire galactic center into a factory for generating the very gravitational waves we began to detect. The sheer scale of this possibility is what makes it so formidable. A single, awakened supermassive black hole at the heart of a merging galaxy could be the central engine behind not just one loud event, but an entire era of sustained gravitational turmoil. It provides a mechanism that explains both the sudden onset and the incredible intensity of the outburst. The quiet zone may have been quiet simply because its central black holes were dormant, its galaxies isolated. The moment that equilibrium was broken, the moment the galaxies began to merge and their central engines roared to life, the entire region was doomed to become the loudest place in the gravitational universe, a testament to the awesome power of the largest and most violent objects in existence. As we push beyond the explanations rooted in known astrophysics, we enter a realm of speculation that challenges the very foundations of our understanding. Some theoretical physicists are asking a question that borders on science fiction. Could the outburst in the quiet zone be a signature not of massive objects colliding, but of space-time itself becoming unstable? This line of thinking ventures into the elusive territory of quantum gravity, the long-sought theory that aims to unify the two great pillars of modern physics, Einstein's general relativity, which governs the very large, and quantum mechanics, which governs the very small. These two frameworks are famously incompatible, and a theory of quantum gravity would represent perhaps the greatest achievement in physics, a complete rewriting of the rules of the universe. The events in the quiet zone might just provide a rare observational clue. General relativity describes gravity as the curvature of a smooth, continuous fabric of spacetime. Quantum mechanics, on the other hand, tells us that at the tiniest scales, the universe is fundamentally grainy and probabilistic, a seething foam of virtual particles popping in and out of existence. Quantum gravity attempts to describe what spacetime itself looks like in this quantum foam. One tantalizing possibility is that under certain extreme conditions, this foam could become agitated, leading to spontaneous, macroscopic fluctuations in the fabric of reality. Think of it like the surface of a calm pond. On a large scale, it looks smooth and continuous, but if you could zoom down to the molecular level, you'd see a chaotic jumble of water molecules constantly vibrating. Now imagine if that microscopic chaos could, just for a moment, bubble up to create a visible ripple on the surface without anything ever touching the water. In the context of the quiet zone, this would mean the gravitational waves weren't produced by colliding black holes, but by space-time itself convulsing, generating ripples from the bottom up with no massive source required at all. How could such a thing happen? The quiet zone, if it were a true cosmic void with an incredibly low density of matter, might be the perfect environment for such an exotic phenomenon. The vast emptiness could allow the quantum fluctuations of the vacuum, which are usually drowned out by the presence of matter and energy, to amplify and coalesce on a macroscopic scale. It's a concept that turns the principle of cause and effect on its head. We are accustomed to waves having a source, a rock thrown in a pond, a black hole merger. This idea suggests that the void itself could be the source, that a profound nothingness might have a dynamics and an energy all its own, capable of erupting into something detectable. The loud zone wouldn't be loud because of what's in it, but because of what it is, or more precisely, what it isn't. Of course, this is highly speculative, a frontier idea that sits far outside the mainstream. The energy required to create space-time ripples large enough to be detected by LIGO from pure quantum fluctuations is staggering, and no current theory provides a robust mechanism for it. Yet, this is how science often progresses. Anomalous data, like the sudden and unexplained roar from a silent patch of space, forces us to consider possibilities we might otherwise dismiss. It encourages a creative leap. Researchers examining this angle aren't claiming to have proof. They are following a fascinating thread of what if to its logical conclusion, using the mystery as a catalyst to explore the furthest limits of our theoretical models. The quiet zone anomaly, in this light, becomes more than just an astrophysical puzzle. It becomes a catalyst for philosophical wonder, pushing us to question whether we truly understand the nature of emptiness and the very stage upon which the cosmic drama plays out. The detection of the gravitational outburst was a monumental moment, but it was only the beginning of the investigation. To truly understand what was happening in that distant region of space, scientists knew they needed more than just the ripples in spacetime. They needed to see it. This is where the revolutionary power of multimessenger astronomy came into play, transforming a one-dimensional signal into a rich, multidimensional story. The moment the gravitational wave alerts went out, a global call to arms was issued across the astronomical community. Within minutes, dozens of the world's most powerful telescopes, each sensitive to a different part of the electromagnetic spectrum, swiveled to focus on the coordinates of the quiet zone, now anything but quiet. This coordinated effort is the heartbeat of modern astronomy. Imagine trying to understand a complex event on Earth, like a volcanic eruption, if you could only feel the vibrations in the ground through your feet. You'd know something powerful happened, but you wouldn't know about the ash cloud, the lava flow, or the lightning in the plume. Gravitational waves are those vibrations in the cosmic ground. To see the full eruption, you need eyes. That's what the telescopes provided. Radio observatories like the Very Large Array in New Mexico scanned for the faint whispers of synchrotron radiation, often produced by jets of fast-moving particles. Optical and infrared telescopes, including the Hubble and Keck observatories, searched for any telltale glow of hot, energized matter or the faint light of newly disrupted stars. Meanwhile, space-based X-ray and gamma-ray telescopes like Chandra and Fermi hunted for the high-energy signatures of the most violent processes in the universe, the sort of energy that only the most extreme objects can produce. The initial results were both thrilling and perplexing. There was no single, brilliant flash of light corresponding to the gravitational wave storm. This immediately ruled out certain types of events, like a supernova or a kilonova from colliding neutron stars, which typically produce a spectacular electromagnetic display. Instead, what the telescopes began to pick up was a more complex and subtle picture. A deep infrared survey revealed a faint but persistent glow coming from what appeared to be a dense, obscured region at the heart of a distant galaxy within the quiet zone. This was a crucial clue. Infrared light can penetrate cosmic dust, and a warm, glowing core is a classic signature of a frenzied environment where stars are forming or dying at an incredible rate, or where a central black hole is actively feeding. At the same time, radio telescopes detected something equally intriguing, a faint, fluctuating source of radio waves. This emission pattern didn't match the steady hum of a normal galaxy. It was more chaotic, hinting at recent, violent activity. By combining the gravitational wave data with these electromagnetic clues, a much clearer narrative began to emerge. The gravitational waves told the story of multiple massive objects merging in a very short period. The infrared glow suggested this was happening in a dense, dusty, and incredibly active nuclear environment, likely the center of a galaxy. The radio waves pointed to ongoing energetic processes, perhaps jets from a central black hole or remnants of the collisions themselves. This collaborative detective work allowed astronomers to piece together a far more complete story than any single messenger could have told alone. It wasn't just about confirming the gravitational wave signals were real, it was about understanding the context. The Multimessenger approach revealed the stage upon which this cosmic drama was playing out. It showed that the loud zone was not some abstract void, but a specific, structured region with a history and an environment that made such a chain reaction of collisions not just possible, but perhaps inevitable. The isolated anomaly of the roaring gravitational data was woven into a coherent story of a dense galactic core, stirred into a violent frenzy, its dark inhabitants colliding in the shadows, their cataclysmic deaths revealed only by the ripples they sent across the universe and the faint, multi-wavelength echo of the aftermath. Word of the discovery spread through the global scientific community with the speed and force of one of the very gravitational waves they were studying. It began in the specialized forums and encrypted collaboration channels where LIGO and Virgo researchers communicate, but it couldn't be contained there for long. The sheer, unprecedented nature of the data, a region of space literally turning its volume from 0 to 11, made secrecy impossible. Preprint papers, those first drafts of scientific discovery, began appearing online within days, their dense text and complex equations trying to frame the unimaginable in academic language. But the excitement bubbling beneath the formal prose was palpable. This wasn't just another data point. It was a paradigm shift happening in real time, and every astrophysicist, cosmologist, and theoretical physicist on the planet wanted a piece of it. The public reaction was an echo of this professional frenzy, amplified through the lens of media and social platforms. Major news outlets, which might normally relegate a complex astrophysics finding to a brief mention in their science section, now led with dramatic headlines and animated simulations of roaring spacetime. Television news programs featured panels of experts trying to explain the significance to anchors who themselves seemed caught between bewilderment and awe. The story had all the elements of a blockbuster, a mysterious silence, a sudden, violent awakening, and the tantalizing possibility of entirely new physics. It transformed the quiet zone from an obscure scientific term into a household name, a symbol of the universe's endless capacity to surprise us. On social media, the phenomenon exploded into a vibrant tapestry of curiosity and creativity. The hashtag Quiet Zone no more began trending globally, accompanied by everything from highly technical threads where amateur astronomers debated dark matter density profiles to surreal memes featuring the universe turning on its subwoofer. Artists rendered stunning visualizations of what the cosmic chain reaction might look like, while science communicators and educators created accessible video explainers that were shared millions of times. This wasn't a passive audience simply consuming news. It was a global town hall meeting with people from all walks of life feeling personally invested in the mystery. They weren't just watching science happen, they were participating in the conversation, their collective wonder fueling a new wave of public engagement with fundamental research. Back in the halls of academia, the reaction was more structured but no less electric. Major international conferences, some months away, hastily added special sessions dedicated solely to the quiet zone anomaly. These weren't dry, technical recitations of data. They were dynamic, standing room-only events that felt more like scientific detective conventions. Researchers presented conflicting interpretations, debated the merits of the Cascade model versus the dark matter collapse hypothesis, and openly critiqued each other's work with a sense of urgent collaboration. The traditional, sometimes slow-paced peer review process was accelerated, with journals fast-tracking relevant papers in recognition of the discovery's monumental importance. This was science operating at its best and most thrilling, a communal effort to solve a shared puzzle, driven by a mixture of fierce competition and profound cooperation. This widespread fascination tapped into something deeper than mere intellectual curiosity. The loud zone became a cultural touchstone because it resonated with a fundamental human experience, the awe of the unknown. It was a powerful reminder that we are living in a golden age of discovery, where our tools are allowing us to perceive the universe in ways that were pure fantasy just a generation ago. The story made people feel connected to the vast, impersonal cosmos in a personal way. It wasn't just about black holes billions of light years away. It was about the human capacity to build instruments that can hear those echoes and the relentless curiosity that drives us to ask why. In the face of the sublime, the quiet zone's roar, therefore, echoed far beyond our detectors. It reverberated through our culture, rekindling a sense of wonder and proving that the greatest stories aren't always found in fiction, but are waiting out there in the dark, waiting for us to learn how to listen. Beyond the immediate scientific scramble to explain the data lies a far more profound and humbling set of questions that this event forces upon us, questions that strike at the very heart of our understanding of reality itself. For centuries, a central goal of science has been to build a predictable and orderly model of the universe, a cosmic clockwork where we can, in principle, know the future state of any system if we understand its present conditions with enough precision. This desire for predictability is more than just a scientific principle. It's a deep-seated human yearning for stability and order in a vast and often incomprehensible cosmos. The quiet zone, in its dramatic and sudden transformation, delivers a powerful challenge to this entire worldview. It demonstrates that the universe is not merely a complicated machine, but a fundamentally dynamic and potentially volatile system, capable of sudden, radical shifts that defy our most careful predictions. This realization carries a significant philosophical weight. If a region of space that we had meticulously catalogued as stable and silent for years can, without any apparent warning, become the epicenter of the most violent gravitational activity we have ever recorded, what does that say about the true nature of the cosmos? It suggests that our maps, no matter how detailed, are always incomplete. They are snapshots of a dynamic reality that is constantly in flux, capable of behaviors we have not yet even begun to categorize. This isn't a failure of science, it is its very essence. Science thrives on these anomalies because they are the points where our understanding is stretched, broken, and then rebuilt into something broader and more resilient. The loud zone is a powerful reminder that the universe is under no obligation to conform to our models of simplicity or predictability. Its rules are its own, and part of our journey is to learn that some of those rules might involve inherent spontaneity. This event also forces a poignant reflection on our own place within this vast and unpredictable tapestry. We exist on a tiny, fragile planet orbiting an average star in a quiet suburb of a galaxy that itself is just one of billions. The events in the quiet zone occurred unimaginably far away and long ago. The waves we detected are ancient messengers from a distant past, yet they have the power to shake the foundations of our knowledge here and now. This highlights a beautiful paradox of human existence. We are cosmically insignificant in terms of scale and time, yet we possess the consciousness and curiosity to reach out across those immense distances and decode the universe's deepest secrets. The loud zone reminds us that we are not just passive observers of a predetermined cosmic play. We are active participants in a grand, ongoing process of discovery, and the universe is a partner in this dance, constantly revealing new layers of its complexity to those who are willing to listen. Ultimately, the story of the quiet zone is a metaphor for the human condition itself. We all build our lives on certain assumptions of stability, that the ground beneath our feet will remain solid, that the sun will rise tomorrow, that the constants of our world will hold. This event, on a cosmic scale, echoes the personal and collective experiences we have when those assumptions are suddenly upended. It teaches a lesson of intellectual humility, encouraging us to hold our conclusions lightly and to remain open to wonder and surprise. The quest to understand the loud zone is not just about finding an astrophysical mechanism. It is part of a much older and deeper human quest to find our bearing in a reality that is far stranger, more dynamic, and more awe-inspiring than we could have ever imagined. It affirms that the universe is not a static backdrop to our lives, but a living, breathing, and sometimes roaring entity, and our never-ending conversation with it is what makes the journey of discovery so profoundly meaningful. The detection of the outburst was a landmark achievement, but for the scientists involved, it felt less like a conclusion and more like a starting pistol firing. The initial data from LIGO and Virgo was like hearing a complex symphony from outside the concert hall. You can tell it's powerful and beautiful, but the walls muffle the individual instruments. To truly understand the composition, you need to be inside with a perfect seat. That's the ambitious goal driving the next phase of this investigation. A global effort to build a new generation of observatories, so advanced they will make our current detectors seem like primitive hearing aids by comparison. The focus is now squarely on the loud zone, and the tools being prepared to study it are nothing short of revolutionary. Leading this charge is a mission that will literally take gravitational wave astronomy to a new dimension, space. The Laser Interferometer Space Antenna, or LISA, is a breathtaking project led by the European Space Agency with NASA collaboration. Imagine taking the principle of LIGO L-shaped interferometer and scaling it up to a truly cosmic proportion. LISA will not be a single observatory on Earth, but a constellation of 3 identical spacecraft, flying in a perfect triangular formation millions of kilometers apart, trailing behind Earth in its orbit around the Sun. This giant triangle will laser beams between its satellites, creating the largest and most sensitive gravitational wave detector ever conceived. By operating in the pristine quiet of space, free from the constant vibrations and thermal noise that plague Earth-based instruments, LISA will open up a whole new low-frequency window on the universe. This is the band where the real monsters sing, the supermassive black hole binaries, slowly spiraling toward each other over millions of years. If the loud zone activity was indeed kicked off by such a colossal merger at its heart, LISA will be the instrument that hears the deep, thrumming prelude to that explosion, potentially tracking the evolution of these binaries long before they collide. While LISA looks to the skies here on Earth, an equally formidable project is taking shape deep underground. The Einstein Telescope is a proposed third-generation gravitational wave observatory, a behemoth designed with sensitivity 10 times greater than our current facilities. Its design is a masterpiece of noise cancellation. It will be built over 1,000 feet below the surface in a geologically stable area to isolate it from even the faintest terrestrial vibrations. Its interferometer arms will be 10 kilometers long, and its design might even involve a triangular configuration with 6 laser beams running in vacuum tubes, allowing it to cross-check its own data and eliminate false signals with unbelievable precision. For the mystery of the loud zone, the Einstein Telescope will act like a microscope for gravitational waves. It won't just detect that a collision happened. It will be able to disentangle the overlapping roar into its individual components, identifying the specific masses, spins, and orbital geometries of every single black hole or neutron star involved in the chain reaction. It could potentially hear the faint echo of the initial trigger, the first merger that started the entire domino effect, and trace the sequence of events with forensic detail. The synergy between these projects is what makes the future so incredibly bright. LISA, sensitive to the low-frequency hum of impending collisions, might provide an early warning system, identifying regions of space that are primed for a future outburst. Then the Einstein Telescope, with its exquisite high-frequency hearing, could be pointed at that region, waiting to capture the detailed symphony of the actual mergers when they occur. This 1-2 punch would transform our understanding from reactive to predictive. We wouldn't just be documenting cosmic history, we'd be starting to watch it unfold in real time. Beyond these giants, other facilities are joining the network. The Kamioka Gravitational Wave Detector in Japan, already operational, and the planned LIGO India Observatory will create a truly global web of detectors, vastly improving our ability to pinpoint the exact location of events and reduce the background noise, allowing the true signal from places like the loud zone to stand out with crystal clarity. The ultimate goal is to move beyond simply detecting waves and into the era of precision gravitational wave astronomy. It's about creating a rich, detailed map of the warped universe. By training these incredible instruments on the loud zone, scientists hope to do more than just choose between the Cascade model and the dark matter hypothesis. They aim to measure the precise properties of the space-time ripples for tiny, telltale signs of new physics, perhaps a faint signature of quantum gravity effects at the event horizon of a merging black hole, or a subtle distortion in the wave pattern that hints at the presence of an unseen dark matter core. The quiet zone's transformation from a cosmic backwater to the main stage of gravitational activity was a gift from the universe, a natural experiment of staggering proportions. The global scientific community is now mobilizing, building the tools we need to not only accept that gift but to unwrap it fully, revealing secrets about the fundamental forces that shape our reality that we can currently only dream of uncovering. One of the most beautiful outcomes of this entire cosmic mystery is how it has reached beyond the confines of professional astronomy and into the hands of the public, transforming everyday people from passive observers into active participants in the discovery process. The story of the quiet zone, with its compelling narrative of silence turning to a roar, is a natural hook for education and outreach. It captures the imagination in a way that abstract equations sometimes cannot, providing a perfect gateway to teach complex concepts about gravity, waves, and the dynamic nature of our universe. Educators at all levels, from elementary school science teachers to university professors, have seized on this event as a living case study. They are using it to show students that science isn't a static set of facts in a textbook, but a vibrant, ongoing detective story where the next chapter is being written right now, and where anyone with curiosity might help crack the case. This spirit of inclusivity is powerfully embodied in the rise of citizen science projects directly connected to the research. Initiatives like Gravity Spy, developed by the LEGO team, invite volunteers from around the world to help sift through the very data that professional scientists are analyzing. The concept is brilliantly simple yet incredibly effective. While advanced algorithms do a great job of filtering data, the human brain remains uniquely skilled at pattern recognition, especially when it comes to identifying subtle or novel types of noise that can masquerade as real signals. On the Gravity Spy platform, volunteers are trained to classify different types of glitches, those pesky instrumental artifacts in the LEGO data. By helping to clean the data and tag these disturbances, these citizen scientists are directly improving the sensitivity of the search for genuine gravitational waves. It's like having a global team of assistants meticulously cleaning the lens of a telescope so the professionals can see the stars more clearly. For someone sitting at home, the idea that they could contribute to cutting-edge astrophysics by spending a few minutes classifying squiggles on a screen is not just empowering, it's a profound democratization of scientific discovery. The impact of this approach goes far beyond just processing power. It forges a deep, personal connection between the public and the cosmos. When a retired engineer in Florida or a high school student in India helps classify a data segment that later contributes to a published paper on the loud zone, they aren't just learning about science, they are doing science. They become part of the collaboration, their effort woven into the fabric of our collective understanding. This breaks down the traditional barrier between the ivory tower of academic research and the wider world, fostering a sense of shared ownership over our exploration of the universe. It sends a powerful message that you don't need a PhD to contribute to humanity's grandest questions. You just need curiosity, a willingness to learn, and an internet connection. Furthermore, this model serves as an incredible pipeline for inspiring the next generation of scientists. A student who gets hooked on classifying glitches for Gravity Spy might be inspired to take more physics and computer science classes, eventually pursuing a career they might never have otherwise considered. They are not just hearing about the scientific method, they are living it, experiencing the thrill of the hunt and the meticulous, sometimes tedious, work that underpins every major breakthrough. The story of the quiet zone, therefore, has a legacy that extends far beyond the immediate astrophysical implications. Its true lasting impact might be measured in the thousands of young minds it ignites, the diverse new voices it brings into the scientific conversation, and the powerful reminder it offers that the universe belongs to all of us, and everyone deserves a chance to listen to its secrets. Pushing the absolute limits of what's technologically possible to detect a ripple in space-time doesn't just expand our knowledge of the cosmos. It sends a wave of innovation crashing into other fields, transforming everything from medical diagnostics to how we process information. The quest to hear the universe's faintest whispers forced engineers and computer scientists to invent tools of almost unbelievable precision, and those tools are now finding life-saving applications right here on Earth. This is the beautiful, often unexpected payoff of fundamental research. We set out to answer a profound question about black holes, and along the way, we accidentally develop a better way to find a tumor. Consider the mind-bending precision required for the mirrors at the heart of LEGO. These are not simple pieces of glass. They are among the smoothest, most highly polished objects ever created by humans, so perfect that if one were scaled up to the size of the continental United States, the tallest imperfection would be less than the height of a doorknob. To suspend these mirrors and isolate them from the constant rumble of our planet, engineers developed a suspension system of incredible sophistication, using fused silica fibers thinner than a human hair. This technology, designed to hold a 40-kilogram mirror so still that it's effectively free from Earth's vibrations, is now inspiring next-generation sensors. Similar vibration dampening systems are being adapted for use in ultra-precise manufacturing of computer chips, where even nanometer-scale vibrations can ruin a microscopic circuit, and in highly sensitive scanning tunneling microscopes that can image individual atoms. The know-how to create a quiet enough environment to hear the cosmos is directly helping us build the quieter, more precise machines that manufacture our future. Perhaps the most significant spin-off lies in the realm of data analysis. The data stream from LIGO is a torrent of information, a chaotic ocean of noise in which the precious signal of a gravitational wave is a single, unique drop of water. Finding that drop required a revolution in computational techniques. Scientists developed advanced machine learning algorithms and noise filtering software that could perform a kind of digital alchemy, separating the mundane vibrations of our world from the cosmic tremors from billions of years ago. These powerful algorithms are now being applied to a much more personal challenge: diagnosing disease. Medical researchers are using these same pattern recognition techniques to analyze complex medical scans like MRIs and CT scans. The software, trained to find incredibly subtle patterns in messy data, can now help radiologists detect the early signs of cancers, neurological disorders like Alzheimer's, or heart disease with a new level of speed and accuracy, spotting faint anomalies that the human eye might easily miss. The code written to find colliding black holes in a sea of noise is now helping to find tumors, potentially saving countless lives. The laser systems themselves are marvels of optical engineering. To measure a change in distance 10,000 times smaller than a proton, LIGO lasers must be phenomenally stable, with a power and purity that were virtually unheard of before this project. The innovations in laser design and control have directly benefited other fields that require extreme precision. In manufacturing, these high-stability lasers are used for ultra-precise metrology, ensuring that parts for everything from jet engines to scientific instruments are made to exacting specifications. In telecommunications, the research has contributed to improving the fiber optic networks that form the backbone of the Internet, allowing for more data to be transmitted with greater fidelity over longer distances. Even environmental monitoring has gained from this work, with new LiDAR systems, light detection, and ranging using these advanced lasers to measure atmospheric pollution and map terrain with unprecedented detail. This cascade of innovation is a powerful testament to the fact that you cannot predict the full return on investment for exploring the fundamental nature of reality. When scientists first proposed building LIGO, they weren't thinking about medical imaging or better manufacturing. They were driven by a pure desire to test a prediction of Einstein's and to open a new window on the universe. Yet, by aiming for a goal that seemed nearly impossible, they were forced to invent new technologies, which in turn spawned new industries and improved countless aspects of our daily lives. The story of the Quiet Zone's roar is not just a tale of cosmic discovery. It is also a story of how that ambition echoes through our society, making us healthier, connecting us better, and building a more advanced world. The technological symphony composed to listen to the stars has found its melody in the most human of endeavors. Solving a puzzle of this magnitude was never going to be the job of a single type of scientist working in isolation. The mystery of the loud zone demanded a kind of intellectual symphony, a concert of diverse minds, each bringing their unique instrument to the performance. This wasn't just a project for astrophysicists. It was a grand challenge that required the combined brilliance of physicists, data scientists, computer engineers, materials experts, and even philosophers, all working in concert. The very nature of the problem ensured that no one discipline could hold all the answers, forcing a level of collaboration that is becoming the hallmark of 21st century science. At the most fundamental level, you had the theoretical physicists, the ones who live in the world of equations and models. Their job was to dream up possibilities, the Cascade mergers, the dark matter collapses, the quantum gravity fluctuations. They built the mathematical frameworks that could explain the how and the why, but a beautiful equation is just a story until it can be tested against reality. That's where the data scientists stepped in, armed with their formidable computational tools. They were the translators, the ones who took the theorists' complex predictions and turned them into digital templates, specific waveforms that could be hunted for within the immense ocean of noisy data from the detectors. They developed the machine learning algorithms that acted like hyper-advanced filters, capable of performing billions of calculations per second to find a single, meaningful pattern. Without their ability to sift signal from noise, the faint initial whispers from the quiet zone would have remained forever lost. Meanwhile, the engineers were the unsung heroes making the entire endeavor physically possible. Their expertise spanned a breathtaking range. Laser engineers designed and maintained the ultra-stable, high-power beams that are the lifeblood of the interferometers. Materials scientists developed the incredibly pure fused silica for the mirrors and the impossibly thin glass fibers from which they are suspended. Seismic engineers designed the multi-stage, active and passive vibration isolation systems that protect the experiment from the constant hum of the Earth. And software engineers built the robust, complex code that controls everything, from the nanometer adjustments of the mirrors to the global network that distributes data and alerts across continents. When the theorists and data scientists needed more sensitivity to hear fainter signals, it was the engineers who answered the call, literally reinventing precision measurement to make it happen. And then, in a beautiful twist, the implications of the discovery drew in thinkers from even further afield. Philosophers of science joined the conversation, helping to frame the deeper questions about cosmic predictability and the nature of scientific discovery itself. Their role was to scrutinize the very process of interpretation, to help the collaboration understand how our human biases and preconceptions might shape the theories we find most appealing. They provided a crucial meta-perspective, asking not just what we were finding, but how we were thinking about what we found. This interdisciplinary tapestry transformed the investigation. A meeting to discuss the loud zone data wasn't a room full of experts who all thought the same way. It was a dynamic forum where a laser engineer could point out a potential instrumental artifact that a data scientist had missed, where a theorist could be inspired by a new noise filtering technique to develop a different model, and where a philosopher could gently remind everyone that the most elegant solution isn't always the correct one. This constant cross-pollination of ideas prevented groupthink and sparked innovation at every turn. The solution to the loud zone mystery won't be found in a single textbook or a single lab. It will be forged in the vibrant, sometimes chaotic, but always productive spaces where different fields overlap and learn to speak each other's languages. It's a romantic notion in science that the greatest discoveries often arrive not through meticulous planning, but through a fortunate accident, a moment of pure serendipity where being in the right place at the right time with the right mindset reveals something astonishing. The story of the Loud Zone is a powerful testament to this very idea. The researchers operating the gravitational wave detectors were not specifically hunting for a silent region to suddenly erupt. Such a concept wasn't even a prominent part of the theoretical playbook. Their primary mission was to catalog known types of events, black hole and neutron star mergers, and to slowly build a statistical map of the universe. The quiet zone was initially just a curious footnote, a blank area on that emerging map that was interesting precisely because nothing was happening there. The team's focus was elsewhere, on the already noisy and active regions of the sky. The discovery of its transformation, therefore, wasn't the result of a targeted search. It was the product of an open-minded approach to data that allowed a stunning anomaly to reveal itself. This underscores a profound truth about how science often truly progresses. We like to imagine it as a linear, logical march from hypothesis to experiment to conclusion. In reality, it's far messier and more beautiful. Some of history's most pivotal moments, from Alexander Fleming's accidental discovery of penicillin in a contaminated Petri dish to the cosmic microwave background radiation found by Arno Penzias and Robert Wilson while troubleshooting pesky radiostatic in their antenna, were stumbled upon by scientists who were prepared to recognize the significance of something they weren't even looking for. In the case of the Loud Zone, it was the graduate student who decided to plot all those tiny, dismissed glitches on a single timeline, or the senior researcher who, instead of deleting an anomalous data run, asked a simple question: what if that's not noise? This is the essence of serendipity in science. It doesn't just hand you a discovery. It presents you with a puzzle, but only if you're paying close enough attention to notice it. Cultivating this environment is a conscious act. The collaborations behind LIGO and Virgo built systems specifically designed to embrace the unexpected. They implemented open data policies, allowing researchers from around the world to access the data streams and apply their own unique perspectives. They created alert systems that would immediately notify astronomers across the electromagnetic spectrum of any potential event, encouraging a culture of rapid follow-up that could catch fleeting surprises. Most importantly, they fostered a psychological environment where questioning the data was not just allowed but encouraged. Junior researchers were empowered to challenge assumptions and pursue weird hunches without fear of being dismissed. This cultural flexibility is the fertile ground in which serendipity can grow. It's the understanding that while we build our experiments to test specific ideas, the universe is under no obligation to comply with our narrow questions, and its most exciting answers often come in the form of questions we were not wise enough to ask. The Loud Zone, therefore, stands as a monumental reminder that the path to knowledge is not a straight line. It is a winding road full of unexpected detours that often lead to the most breathtaking vistas. It argues for a science that values curiosity-driven exploration just as much as goal-oriented mission planning. It tells us that the most important tool in any observatory isn't the laser or the mirror, it's the human mind behind it, a mind that remains open, curious, and forever willing to be surprised. The greatest discoveries await not just those who seek answers, but those who are wise enough to always be listening for the unexpected question. What makes the Loud Zone so compelling isn't just its own bizarre story, but how it echoes a pattern we've seen time and again throughout astronomy, a pattern of profound cosmic silence being suddenly and violently broken. This theme of the universe switching from a whisper to a scream connects this gravitational wave anomaly to some of the most enduring and thrilling mysteries in modern astrophysics, suggesting that we might be glimpsing a fundamental, yet poorly understood, behavior of the cosmos. Perhaps the most famous contemporary example is the phenomenon of fast radio bursts, or FRB. For years, astronomers listening to the radio sky noted these incredibly brief, incredibly powerful blasts of energy, each one lasting mere milliseconds but releasing more energy than the Sun does in 80 years. Initially, they were seen as isolated, one-off events, seemingly random and utterly mysterious. But then, researchers began to find repeating FRBs. A source would fire off a single brilliant burst and then fall silent for years, only to suddenly reactivate and spit out a whole series of flashes in a matter of hours or days. This transition from a single, enigmatic event to a period of frantic, repeated activity is a direct parallel to the quiet zone's journey. In both cases, a source we initially categorized as a rare fluke revealed itself to be capable of volatile, storm-like outbursts, forcing us to completely rethink what kind of cosmic engine could possibly switch on and off with such staggering power and speed. We can look even deeper into the universe's history to find another powerful comparison: the mystery of reionization. For hundreds of millions of years after the Big Bang, the universe was a dark, quiet, and simple place. It was filled with a fog of neutral hydrogen gas, and not a single star or galaxy had yet formed to light it up. This period is rightly called the Cosmic Dark Ages. Then, quite suddenly on a cosmic timescale, everything changed. The first stars and galaxies ignited, and their intense ultraviolet radiation began to burn away the fog, ripping electrons from atoms in a process called reionization. This was the universe's own Great Awakening, a transition from a silent, opaque state to a transparent, structured, and brilliantly lit cosmos filled with complex structures. The scale is unimaginably larger, but the fundamental narrative is the same as the loud zone. A long era of featureless tranquility giving way to a sudden, transformative, and violent period of activity that permanently alters the landscape. It shows us that these phase changes, these cosmic transitions from quiet to loud, are not bugs in the system. They appear to be a fundamental feature of how our universe evolves at every scale. Perhaps the most profound parallel lies with the greatest puzzle of all: dark energy. For the first half of the universe's life, the gravitational pull of all matter, both dark and visible, was slowly putting the brakes on the expansion following the Big Bang. Everything was gradually slowing down. Then, around 5 billion years ago, something extraordinary happened. The expansion of the universe against all expectations started to accelerate. It was as if a silent, invisible pressure that had been present all along suddenly overcame gravity and began to push the cosmos apart at an ever-increasing rate. We call this mysterious force dark energy, and its discovery was a shock that completely upended cosmology. This is the ultimate example of a silent background actor suddenly taking center stage with dramatic consequences. For billions of years, its effect was negligible, a whisper in the data. Then, at a certain point, it became the dominant force shaping the entire fate of the cosmos. The quiet zone's outburst is a localized, specific version of this same theme, a hidden potential for dramatic change that lurks beneath a veil of calm, waiting for the right conditions to express itself with overwhelming force. By drawing these connections, we do more than just create a list of interesting mysteries. We start to build a unified framework for understanding cosmic volatility. It encourages astrophysicists to look for common underlying physics. Could the mechanisms that trigger a fast radio burst be a scaled-down version of the processes that ignited reionization? Could the chain reaction in the loud zone be governed by principles similar to the phase change that allowed dark energy to dominate? This comparative approach is a powerful engine for scientific progress. It allows researchers to borrow insights from one field and apply them to another, creating a cross-pollination of ideas that can break a logjam. The story of the loud zone is no longer an isolated oddity. It becomes a crucial data point in a much larger investigation into the rhythms of the universe, a single, powerful note in a grand cosmic symphony of silence and sound that helps us understand the music as a whole. Behind every data point in the loud zone mystery, behind every alert that flashed across a screen and every complex waveform that needed decoding, there was a person. This wasn't a story told by machines. It was a human story written in late-night coffee runs, sudden gasps of realization, and the quiet, persistent dedication of individuals whose names you'll likely never know. To understand the true weight of this discovery, you have to step away from the cosmic scale and into the control rooms and university offices where the real drama unfolded. Imagine a graduate student, let's call her Anya, who had spent the better part of her PhD thesis analyzing the quiet zone. For years, it was her personal academic quagmire, a source of frustration and fascination. She knew its silence better than anyone, had catalogued every conceivable reason for its tranquility. The day the first significant blip appeared on her specialized monitoring feed, her reaction wasn't excitement but profound annoyance. She was certain it was a glitch, another hours-long detour into debugging and calibration logs. But as the pattern persisted, that annoyance melted into a kind of nervous, electrifying focus. She described it as the feeling of watching a sleeping giant take its first deep breath, a moment where pure scientific curiosity became a personal, heart-pounding vigil. Across an ocean, a senior data scientist named Ben was wrestling with a different piece of the puzzle. His role was to maintain and improve the intricate algorithms that filtered the detector's noise. When the outburst began, his initial triumph that the systems were working was quickly replaced by a new challenge. The signals were so numerous and overlapped so dramatically that they were threatening to overwhelm the very software designed to find them. He recalls a 48-hour period where he and a small team essentially lived in the lab, surviving on pizza and a sense of shared mission, rewriting code on the fly to handle the unprecedented data deluge. For him, the loud zone wasn't an abstract cosmic event. It was a supremely stressful and exhilarating software update, a race against time to ensure the instruments could keep up with the universe's sudden loquaciousness. His story is a reminder that for every elegant theory, there are countless hours of gritty, technical problem-solving happening in the background. Then there are the telescope operators, the unsung sentinels of the sky. At observatories around the world, from the high deserts of Chile to the peaks of Hawaii, these individuals received the automated alerts from the gravitational wave network. For many, it meant canceling carefully planned observation schedules for other projects instantly, pivoting their powerful instruments to focus on a set of coordinates that, just hours before, would have been considered a waste of precious telescope time. One operator described the surreal experience of slewing a billion-dollar telescope to stare at a patch of sky that was, to all conventional instruments, still utterly dark and unremarkable. They were pointing their tools at emptiness based on a message from a different kind of sense entirely, an act of faith in a collaborative, multi-messenger vision of the universe. Their personal stake was in the silence that followed, the tension of waiting for any flicker of light to confirm what the gravitational waves were screaming. These personal stories coalesce into a powerful narrative about modern science itself, the image of the lone genius having a eureka, a moment in isolation, is a relic of the past. The investigation into the loud zone was a profoundly collective endeavor. It involved thousands of people, from the engineers who polished the mirrors to the theorists who ran the simulations, from the PhD students who wrote the first draft of the paper to the administrators who secured the funding to make it all possible. A project manager for the collaboration spoke of the emotional whiplash of guiding such a diverse, global team through the roller coaster of the discovery, from the initial skepticism, through the feverish excitement, and into the long, meticulous grind of validation and publication. For them, the greatest achievement wasn't just the scientific result, but the proof that such a vast and varied group of humans could unite with a single purpose, transcending borders, languages, and disciplines to achieve something no one could have done alone. The loud zone's roar was detected by machines, but it was understood by people, and its legacy is as much a testament to human collaboration as it is to cosmic violence. To truly understand what might be happening billions of light years away, scientists are building entire universes inside supercomputers. This is the world of computational astrophysics, where the impossible becomes testable through the sheer power of simulation. When the first gravitational wave alerts from the loud zone lit up their screens, researchers didn't just look through telescopes, they rushed to their workstations to run digital experiments. These aren't simple animations, they are incredibly complex numerical models that solve the fundamental equations of physics: general relativity, hydrodynamics, magnetohydrodynamics, all at once across mind-boggling scales of both size and time. They allow scientists to take a compelling idea, like a chain reaction of black hole mergers, and ask the computer a simple but profound question: if we set up these initial conditions, what happens next? One of the primary simulations used to test the Cascade theory involves creating a virtual dense cluster of stars. Researchers start by defining the parameters: the number of stars, their masses, the initial density of the cluster, and the velocity distributions. The computer then sets this digital cluster in motion, calculating the gravitational pull between every single object over millions of years of simulated time. In these crowded environments, stars inevitably interact. They don't often collide directly, but their paths can be drastically altered by close encounters, a process known as gravitational scattering. The most massive stars evolve quickly, exploding as supernova and leaving behind black holes and neutron stars. Because of their immense weight, these remnants sink to the center of the cluster through a process called mass segregation, forming a dense nucleus of dark, massive objects. The simulation then watches this nucleus. Binary pairs of black holes form and begin to inspiral, emitting gravitational waves. The key question is whether the environment is volatile enough to trigger a domino effect. In some model runs, the cluster remains relatively stable for the entire simulation, but in others, a single merger provides the necessary spark. The new, more massive black hole created by that first collision can receive a kick from the anisotropic emission of gravitational waves, sending it recoiling through the heart of the cluster at hundreds of kilometers per second. This kicks over the apple cart, violently perturbing the orbits of other binary systems. The simulation shows these disturbed binaries tightening their orbits faster, leading to a rapid succession of mergers within a very short astronomical time frame. The output of this simulation isn't just a movie, it's a data stream of predicted gravitational waveforms. Scientists can then compare this simulated data to the actual, complex signal from the loud zone, looking for a match in the timing, the amplitudes, and the frequencies of the overlapping waves. A good match doesn't prove the theory, but it shows that the proposed mechanism is not only possible but produces a realistic outcome that mirrors our observations. Other teams are running vastly different simulations to test the dark matter hypothesis. These models are even more complex, as they require making assumptions about the unknown properties of dark matter itself. One simulation might model the quiet zone as containing a large, diffuse halo of cold dark matter. Another might seed it with a more concentrated clump of self-interacting dark matter particles. The simulation then runs for eons of virtual time, watching how this dark matter distribution influences the normal baryonic matter, the gas and stars in the region. The goal is to see if the dark matter's gravity can, over time, shepherd stellar mass black holes into such a dense configuration that a cascade of mergers becomes inevitable. The simulation checks for telltale signs. Does the dark matter cause a sufficient increase in the density of black holes? Does it affect the rate at which they form binary pairs? The gravitational wave signal predicted by these dark matter-driven models can have subtle differences, perhaps in the distribution of black hole masses or the spin orientations of the merging objects, providing a potential fingerprint that could be hunted for in the real data. Perhaps the most critical role of these simulations is their power to rule ideas out. A theorist might propose an exotic quantum gravity effect as the source of the waves. Before such an idea gains any traction, it can be put to the test in a simulation. The researchers would encode the proposed mathematical rules of this new physics into their model and run it. If the simulation consistently produces results that look nothing like the observed data, or if it requires physically impossible initial conditions to work, the idea can be gently set aside, allowing the community to focus on more plausible scenarios. This iterative process of simulation and comparison is how astrophysics narrows down the infinite possibilities of the cosmos to a handful of likely truths. It turns the loud zone from an impenetrable mystery into a solvable problem, giving us a digital sandbox where we can replay the birth of a gravitational storm again and again until we finally understand the conditions that created it. This incredible discovery, one that rewrote our map of the cosmos, could never have been made by a single nation or a solitary team of researchers working in isolation. The very nature of gravitational waves demands a global perspective. These ripples wash over the entire Earth, and to catch them requires a network of ears listening from different corners of the world, their combined efforts separating the cosmic truth from the mundane noise of our planet. The investigation into the loud zone was a testament to this fact, a symphony of international collaboration where the most beautiful note was the sound of borders dissolving in the name of a shared quest for understanding. At the heart of this effort are the observatories themselves, a family of instruments scattered across the globe. The twin LIGO detectors in the United States, separated by 1,860 miles, provide the essential first step of verification. If a signal is real, it will show up in both Louisiana and Washington state with a tiny time delay. But 2 points are not enough to pinpoint a location on a sphere. This is where the Virgo detector in Italy becomes indispensable. By adding a third listening post on a different continent, the network can use the technique of triangulation. The minute differences in the arrival time of a wave at each facility allow scientists to trace its path back to a specific patch of sky, much like how your 2 ears can tell what direction a sound is coming from. For the quiet zone, this triangulation was the crucial first clue that those faint, early whispers were indeed originating from that specific, silent region and not from some instrumental ghost. But the family is growing. The Kamioka Gravitational Wave Detector, or KAGRA, in Japan has joined the hunt, built deep inside a mine to benefit from the incredible seismic quiet of its underground home. Soon, it will be joined by LIGO India, a new observatory that will complete a truly planetary-scale network. With 4 or 5 major detectors operational, the ability to locate a source will become exquisitely precise. This means that when the next cosmic event shakes space-time, Astronomers using traditional light-based telescopes will know exactly where to point their instruments within minutes, dramatically increasing the chance of capturing a multimessenger event. This isn't a competition, it's a relay race where each nation's contribution makes the entire team faster and more capable. The collaboration extends far beyond the physical hardware. It lives in the daily rhythm of the research teams. The data from every detector is pooled into a common archive, accessible to scientists within the global partnership regardless of their nationality or home institution. A researcher in Germany can analyze data from Louisiana. A student in Australia can write code to process signals from Japan. The work is coordinated across time zones, with major decisions made in large, virtual collaboration meetings that might have hundreds of participants dialing in from a dozen different countries. These meetings are a testament to the collective spirit, a place where a senior professor from the United States might have their hypothesis gently challenged by a postdoctoral researcher from India, with the best idea winning out not because of seniority or title, but because of the strength of its evidence. The language of this collaboration is a unique blend of specialized English, the lingua franca of modern science, and the universal language of mathematics and physics. This model of open, international science is a powerful counter-narrative to the divisions that often dominate world affairs. It proves that humanity can still unite around a common, awe-inspiring goal that offers no immediate military or economic advantage, only the profound reward of knowledge. The funding for these projects comes from the taxpayers of multiple nations, from America and Italy, from Japan and India, from the Netherlands and the United Kingdom, each country investing in a shared vision of exploration. They are not funding an instrument that belongs to one nation, but contributing a vital piece to a global sensor that belongs to all of humanity. In an era of complex global challenges, from climate change to pandemics, the gravitational wave community stands as a shining example of what is possible when we choose collaboration over competition, building a network of understanding that is as vast and interconnected as the space-time it seeks to measure. The sheer volume and complexity of the data pouring in from the loud zone was unlike anything the scientific teams had ever encountered. It wasn't just a single, clean signal to analyze. It was a cacophonous roar, a dense thicket of overlapping gravitational wave chirps where multiple events were happening almost simultaneously, their signals interfering with and amplifying each other. This presented a monumental interpretive challenge. The existing data analysis pipelines, which were brilliantly designed to pick out individual events from a quiet background, were completely overwhelmed. It was the astrophysical equivalent of trying to hold a conversation with a single person in a silent library versus trying to pick out that same person's voice in a roaring, packed stadium during the final moments of a championship game. The standard tools simply weren't built for this level of chaos. The first and most daunting hurdle was what scientists call the cocktail party problem. How do you separate one voice from a crowd of people all talking at once? In gravitational wave terms, each merging black hole or neutron star pair has a unique voice, a specific waveform defined by the masses and spins of the objects. When these voices all shout at the same time, their waveforms add together into a single, incredibly messy and complicated data stream. Disentangling this single roar back into its individual components required a fundamental leap in statistical and computational methods. Researchers had to develop new algorithms that could essentially perform a form of digital audio separation, but for space-time itself. These new techniques didn't just look for one signal at a time. They were designed to search for many signals at once, testing millions of different combinations of waveforms to find the set that, when added together, most closely matched the chaotic data they were seeing. This process demanded an almost unimaginable amount of computational power. A single second of data from the loud zone could require weeks of processing time on a supercomputer as it ran through countless possibilities. To make this even remotely feasible, scientists turned to machine learning, training neural networks on simulated data of overlapping signals. They essentially created a digital apprentice by feeding these networks examples of what a cacophony of 10, 20, or even 30 overlapping gravitational wave events might look like. Over time, the neural networks learned to recognize the subtle fingerprints of individual events within the noise, becoming incredibly adept at making initial guesses that the more traditional but slower algorithms could then refine. This human-AI collaboration became the new standard, a necessary partnership to tackle a problem of such staggering complexity. Beyond the statistics, there was the equally difficult challenge of simply visualizing this mess. How do you present this data in a way that the human brain can begin to comprehend? Traditional plots showing a single wavy line on a graph were useless. The solution came from borrowing techniques from other fields. Data visualization experts began creating intricate three-dimensional models with time on one axis, frequency on another, and the wave amplitude represented by color and brightness. These visualizations looked less like scientific graphs and more like vibrant, abstract topographical maps of a mountain range that was constantly convulsing. Scientists could then fly through this data landscape, visually identifying clusters of activity, spotting patterns in the chaos, and literally seeing where the loudest peaks were located. This shift from a one-dimensional line to a rich, multi-dimensional landscape was a breakthrough in intuition, allowing researchers to develop a gut feeling for the data that pure mathematics could not provide. Each proposed solution, however, introduced its own new set of problems. The powerful new algorithms were so sensitive that they began to find ghost signal statistical mirages that looked real but were just random fluctuations in the noise lining up in a convincing way. The visualization techniques, while beautiful, could sometimes create optical illusions, making researchers see patterns that weren't actually there. This forced the teams to implement even more rigorous validation checks. They would often inject fake signals into the real data stream, creating a blind test to see if their methods could recover the inserted signals without being fooled by artifacts. It was a painstaking, iterative process of trial and error, of building a new tool, finding its flaws, and then building a better one. This process is the unglamorous engine of scientific progress, a relentless cycle of doubt and refinement that ensures that by the time a result is announced, it has survived the most brutal gauntlet of scrutiny imaginable. The story of interpreting the loud zone is a powerful testament to the fact that in science, the answer is rarely just sitting in the data waiting to be found. More often, you have to invent entirely new ways of seeing before the truth can reveal itself. The sheer scale of the event unfolding in the quiet zone is almost impossible to fully grasp with our everyday human perspective. We measure these gravitational waves in terms of energy, and the numbers become so astronomically large that they lose all meaning. The outburst released more energy in a matter of days than all the stars in 100 galaxies would emit in the same amount of time. This wasn't just a few firecrackers going off in the void. It was a sustained, cosmic detonation of almost inconceivable power, all originating from a single patch of sky that had previously shown nothing at all. To produce ripples in space-time strong enough to be detected across billions of light-years, the collisions involved objects of staggering mass, black holes many times heavier than our Sun, whirling around each other at a significant fraction of the speed of light before smashing together in a final, violent merger that momentarily shook the very fabric of the cosmos. And yet, the most humbling part of this story is not the raw power on display, but the incredible distances involved and the ancient history we are witnessing. The quiet zone isn't just far away, it is profoundly, almost philosophically remote. The gravitational waves that finally reached our detectors began their journey across the universe long before our planet even existed. They raced through the void while Earth was still a molten rock, while the first single-celled organisms were stirring in the oceans, while dinosaurs ruled the land and then vanished. These ripples have been traveling for hundreds of millions, perhaps even over 1 billion years, carrying a message from an epoch so distant that the continents on our own world were arranged in a completely different configuration. We are not observing this event as it happens now. We are receiving an echo from a past so deep it predates most complex life on our planet, a delayed broadcast from a time when the universe itself was younger. This incredible time lag highlights our unique and poignant place in the cosmos. We are, on the grand cosmic scale, inconceivably small and temporary. Our entire world is a fragile, blue-green oasis orbiting an average star in a quiet suburb of a galaxy that contains hundreds of billions of other stars. Our civilization, with all its triumphs and tragedies, has existed for less than a blink of an eye in cosmic terms, and yet here we are. This tiny, fleeting species, perched on a speck of rock and water, has managed to build machines of such exquisite sensitivity that we can reach out across those mind-numbing gulfs of space and time and feel the faint tremors from collisions of monsters that died eons ago. We have developed the mathematics to understand these signals and the curiosity to care about what they mean. There is a beautiful paradox in this. Our physical insignificance is matched only by our intellectual ambition. The universe is vast beyond comprehension, often violent and utterly indifferent to our existence, but we possess the consciousness to perceive its grandeur and the courage to try and understand it. The transformation of the quiet zone serves as the ultimate reminder that the cosmos is not a static painting but a dynamic, evolving, and often violent reality. What we perceive as the fixed and silent starscape above us is an illusion. The universe is alive with activity, constantly changing, with titanic events unfolding all the time, hidden from our ordinary senses. A region can sleep for 100 million years and then, in a geological instant, explode into a frenzy of creation and destruction. This dynamism isn't an exception, it is the rule. Stars are being born in stellar nurseries, others are dying in spectacular supernova, galaxies are colliding and merging, and black holes are dancing their fatal dances in the dark. The loud zone pulled back the curtain on this endless cosmic drama, giving us a front-row seat to a show of force that reminds us we are living in a universe that is very much awake, a place where the only constant is change itself, happening on scales and timelines that both dwarf and define our fleeting existence. While the cascade of collisions and the potential role of dark matter offer compelling explanations grounded in known astrophysics, the sheer extremity of the loud zone's outburst has led some of the most adventurous minds in theoretical physics to ask a far more radical question. What if the answer doesn't lie in things we already suspect are out there, like black holes or dark matter, but in something entirely new? This line of thinking pushes beyond the edges of our current maps of reality, into the realm of speculative physics where anomalies like the loud zone are not just problems to be solved, but potential signposts pointing toward a deeper, richer understanding of the universe's fundamental rules. One particularly thrilling idea involves the possibility of entirely new fields of energy or exotic particles that we have not yet dreamed of. The standard model of particle physics, while incredibly successful, is known to be incomplete. It doesn't include gravity, for one, and it offers no candidate for the dark matter that we know must exist. Could the loud zone be a laboratory for something even more unusual? Some theorists speculate that a region of space might temporarily become unstable due to the presence of a previously unknown field, a kind of cosmic energy that can spontaneously trigger the release of gravitational waves without any massive objects colliding at all. Imagine a bottle of soda that's been shaken. It remains stable until a tiny disturbance causes it to fizz over explosively. In this analogy, the quiet zone wasn't empty. It was a cosmic bottle that had been shaken by some unseen energy field, and the outburst was the universe finally popping the cap. Another frontier concept involves the search for what physicists call beyond the standard model particles. We're familiar with particles like electrons and quarks, but what if there are others that interact with normal matter only through gravity, making them effectively invisible to every other type of detector we've ever built? These hypothetical particles with names like actions or gravitinos could have accumulated in vast numbers within the quiet zone. If they were to suddenly decay or annihilate each other, they could release an enormous amount of energy in the form of, you guessed it, gravitational waves. This would mean the loud zone wasn't loud because of what was in it, but because of what it was made of. A vast cloud of invisible particles finally reaching a tipping point and converting their mass directly into space-time ripples. Perhaps the most mind-bending speculation of all connects the loud zone to the mysteries of the very early universe. Cosmologists believe that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion called inflation. This process is thought to have been driven by a mysterious inflationary field. While this field is believed to have decayed long ago, some theories suggest that remnants of it could still exist, trapped in certain regions of space like cosmic fossils. If the quiet zone contained such a pocket of this primordial energy, and if it suddenly decayed or underwent a phase transition, like water freezing into ice, the release of energy would be cataclysmic, easily capable of generating the gravitational storm we observed. This would make the loud zone not a recent anomaly, but a window into the universe's first moments, a place where a piece of the Big Bang itself finally finished unraveling. This willingness to entertain such wild ideas is not a sign of desperation, but a testament to the scientific process at its most creative. Major breakthroughs in physics have always been preceded by anomalies that stubbornly resisted conventional explanation. The odd orbit of Mercury hinted at the flaws in Newtonian gravity, paving the way for Einstein's general relativity. The inexplicable stability of atoms led to the development of quantum mechanics. The loud zone could be a similar catalyst. By daring to consider explanations from outside the established playbook, physicists are not abandoning rigor, they are expanding the playing field. They are using this one spectacular event as a reason to ask the biggest questions of all, reminding us that the universe is likely far stranger, more wonderful, and more full of secrets than we have so far dared to imagine. Even before the final chapter of this mystery is written, the story of the quiet zone has irrevocably altered the landscape of modern astronomy. Its legacy is not just about solving a single puzzle, but about how it has reshaped the very process of scientific discovery, leaving a profound and lasting mark on how we observe, interpret, and ultimately understand the cosmos. This event serves a dual role. It is both a specific, high-value case study for astrophysicists and a powerful, universal symbol for the spirit of scientific inquiry itself. As a case study, the loud zone has become a new benchmark, a Rosetta Stone for deciphering extreme cosmic environments. It provided the first rich, complex dataset of a gravitational wave storm, a treasure trove of overlapping signals that forced the development of entirely new analytical tools. The algorithms born from the struggle to untangle this cosmic cacophony are now standard tools in the data scientist's kit, being applied to other messy astrophysical problems, from mapping the faint background hum of all the universe's mergers to cleaning up data from radio telescopes. The collaborative Multimessenger response, the rapid global coordination between gravitational wave detectors and electromagnetic telescopes, has been refined into a well-oiled machine. The protocols established during those frantic first hours of the outburst are now the gold standard for how the astronomical community responds to any new, unexpected event, ensuring that the next surprise will be met with even greater efficiency and coordination. More fundamentally, the loud zone has instilled a new humility and a renewed sense of wonder into the field. It shattered the comfortable assumption that we could easily categorize regions of the universe as active or quiet. It taught us that cosmic silence is not a permanent state, but a phase, a lesson that is now being applied to other mysteries. Astronomers are now re-examining other so-called quiet patches across the electromagnetic spectrum with fresh suspicion, wondering if their tranquility is also just a prelude, asking what might be brewing in the darkness that we simply lack the senses to perceive yet. This event has effectively rewritten the textbook on cosmic volatility, adding a new chapter on how suddenly and dramatically a region can transform. Beyond its immediate scientific utility, the loud zone has become something more, a potent symbol. It embodies the beautiful, iterative, and unpredictable nature of the scientific journey. It is a classic example of a serendipitous discovery. Researchers were looking for one thing and found something utterly unexpected and far more fascinating. It stands as a powerful reminder that the universe is under no obligation to conform to our models, and that the most exciting discoveries often lie in the anomalies, the data points that don't fit, the whispers that defy easy explanation. This story perfectly illustrates that science does not advance in a straight, predictable line from question to answer. Instead, it lurches forward in fits and starts, driven by curiosity, stubbornness, and a willingness to be proven wrong. The most enduring legacy of the quiet zone may be its role as a catalyst for curiosity in the public imagination. It provided a narrative that resonated deeply, a mystery, a dramatic change, and a global effort to solve it. This single story did more to explain the dynamic, evolving nature of the cosmos than a dozen textbooks could. It demonstrated that science is not a dusty collection of settled facts, but a living, breathing process of exploration. It showed that even our most advanced instruments are still just giving us a first glimpse of a reality far stranger and more wonderful than we imagined. The quiet zone's transformation from a cosmic backwater to the main stage of gravitational activity will forever stand as a landmark moment, not because it provided all the answers, but because it taught us how to ask better, bolder questions of the